Hi, welcome to your lesson on applied sequences and series. We're going to look at some compound interest and population growth problems. These were the problems that were selected from the homework, which students said were difficult, particularly these two problems, but also these three were requested. Let's take a look. Okay, first of all, these are the formulas we will need. There's the simple interest formula. There's the compound interest formula, which is just another version of this one. And there is the population growth formula, which is just a geometric sequence. Let's take a look. Here's number one from the first exercise. It says, for each final amount given below, calculate the amount of interest paid or earned. In the first example, it gives you a dollar amount, a simple interest, and it says it's paid annually for 10 years. Well, that's pretty straightforward. You use the simple interest formula because it says it's simple interest. You put in your starting amount, you put 1 plus the rate multiplied by the number of years, 10, and you get your answer. In the second one, a student asked, why isn't the number of compounds per year, let's see, simple interest of, okay, it says, why isn't the number of compounds stated? In the first one, it says it's paid annually, but here it doesn't say if it's paid annually, it just says it's paid for 8 years. So maybe when it just says paid for 8 years, you can assume it's paid annually. But when you look at the answer here, taken from the answer booklet, you notice they take the rate here and divide by 4. So basically, it looks like there was an assumption here that this is paid out 4 times a year or quarterly, and that's what's happening here. So we have a quarterly payment, and then you can see here also the 8 years has been multiplied by 4 to give 32 total payments of a rate that has the annual rate divided by 4. So anyway, I can see the confusion there. There's something missing in this problem here. This is a new textbook, and these things will happen. There will be errors like that. All right, so again, here's the number of payments per year. It is not specified, and the answer seems to show that the payments are quarterly, which I just mentioned. Okay, let's take a look here. Number 5, you invest 5,000 Swiss francs. And today, in an investment that pays 3.25% per annum or per year, compounded monthly, so it will be paid 12 times. How long will it take for the investment to double in value, assuming no additional withdrawals or deposits? Okay, so the investment has to double. So we're going to use the compound interest formula because it's compounded here. And we're going to put in what we know. We know the initial amount is 5,000. So the principal or initial amount goes here. There's a 5,000. Our goal in this investment, here's what the investment produces, right? And here it says how long will it take it to double. So here is the goal of this investment. You want to know when this 5,000 will turn into 10,000. So that's the doubling there. So that's basically from this statement here, you can begin with that. And here you just fill in the rest. 1 plus the rate, here's 3.25% interest divided by 12 because it's compounded 12 times in the year. And here we have 12 times, and then the number of years, which is unknown. We don't know how many years it will take to reach this amount. Next step, we can divide both sides by 5,000. We get 2 here. All this here has been simplified into this, and there's our 12t. So now we have a situation, we have an exponent has a value that is unknown. We can use logarithms, but right now this textbook assumes you don't know logarithms. But let's just remind ourselves how to do that, because we did a bit of that last year. So here we have log of 2. And on this side, we put log as well. So we do log of this side equals log of this side. But notice on this side, this exponent has jumped in front of the log here. So as you may remember, when you have log and log here, you can drop exponents. That's one of the powers of a log. It allows you to drop the exponent. So the exponent has been dropped down. Now we can solve for t. So t equals this thing divided by 12 and this log here. So t is log 2 divided by all of this moves to that side. And that gives us a value of 21.4. So it will take 21.4 years. However, in this one, if you do not know logs, there's ways to do this on our calculator. And it's quite a nice feature of the calculator, and it lets us get answers like this quite easily. So let's check how to do it. So here's the calculator. We're going to turn it on. And basically where you begin is by putting this function into your calculator. we want to know when this function here, or this equation, will produce this value. So I'm going to put this function in and see what happens. So y equals, I'm going to put that in as a function here, or an equation. Y equals 1.02, nope, sorry, I forgot a 0 there, 0.27083 to the exponent 12, and since I'm using y and x here, I'm going to put x here. Okay, now usually we can graph things like that, right? We can graph that, we can see our graph here. We know this is exponential, so we can see this is growing exponentially, but slowly. So we know already, we can see this is not rising so fast, and we know from the logs that our answer is 21. So eventually this will have to go to 21 here to get the value we need. This is kind of the slow way to do a graph, because when you have a graph, you can do trace, for example, and you can move the cursor along the graph. So I just press trace. I'm moving the cursor, and it says, look, x equals 2, y equals 1.07. But we want the answer to this equation, or the y value, to be 2. So y values are 1.07 right now. Going really slowly. Eventually we'll get to 2, I guess. The y value will get to 2. If you kept going like that, eventually you would see the x value that produces a y value of 2. So we'll see the t value, or the x value, that produces a y value of 2. But it's taking forever. All right, so there's another way to do this as well. When you have an equation entered into your calculator, you can either graph it, or you can press second, and the same button as graph says table. When you press table, now you can see a table of values for your graph. So it shows you a bunch of x values and the corresponding y values. And this seems to begin at 20. That means my settings are set up somehow. The way to set the table, just like if you, so let me just quit here. If you had a graph, you know when you have a graph, you can change, right here is the window, and you can change what part of the graph you're looking at, right? You can change what x values, what y values, like what is this window here that we're looking at the graph from. Same thing with the table. So if I go to table, here's my table again. I can go second, and instead of doing windows, second table set, right there, TBL-SET. Table set, it allows me to set the table. It says, where do you want to start the table? So let's say I just started it at 10, and then this change, this triangle means delta table. Change in table means what do you want the x values to go up by? Well, I'm looking for an answer in years here, so I'm going to make the x values go by ones. So I'm going to keep a 1 there. I'm going to make the table start at 10. Now I'm going to go back to the table, second table. Now I have a table. So you start at 10, and these x values are jumping by 1, and then I can see what the y values are. So when x is 10, y is this, when x is 12, and so on. I can scroll down the table, and all of a sudden, I can see the y values right here. They go from 1.97 to 2.04. And you look at the x values. So somewhere between 21 and 22, the x values produced a y value of 2. So that tells me somewhere between, right? And we know our answer is 21.4. You can be more specific in the table. So if I go second table set, now that I know it's between 20 and 21, I can begin at 20, and I can make the numbers that the x jumps by be much smaller. I can make them by 0.1, for example. By 0.1, so I go table, and now you can see here's 20, 20.1, 20.2, 20.3, and so on, until if you keep scrolling down, here it is. 21.3 is that, and 21.4 is that. So we can basically say, yeah, about 21.4. So that's a table feature. Hope you find that useful. All right, so that's that question. Let's go on to number 8. Number 8 is one that everybody said was difficult. Let's take a look. It said Ahmed has 40,000 Egyptian pounds to invest. He wants to split his money equally between a savings account with a simple interest and a 2-year guaranteed investment. Okay, so anyway, he's taking 40,000, splitting it between 2 accounts. That means he's putting 20,000 in each. The first account is a simple interest account. So we're going to use the simple interest formula to figure out how much money he's making in this first one. All right, so he puts in 20,000, which is half that money. And then simple interest, you do 1 plus the rate, and then n is the number of years here. And does it say how many years? It doesn't. So we're going to leave that as that. Then we're going to look at the second account that he's putting money into, which is the this guaranteed investment certificate. It has an interest rate of 3.5, compounded monthly. Okay, so let's put that in here. So now he's putting 20,000 in that one also. There's the 3.5% compounded monthly divided by 12. And it says this one is a 2-year guaranteed investment. So this will only happen for 2 years. So here we do put the 2 years. And then that means we can calculate the value of this. Because the question in the end says, how long will he have to leave the money in the savings account? That means this one. So it earns the same amount as the GIC. So when will this produce the same amount as this? This one we can calculate the amount. So if I follow through and multiply all that, I get this value. So this special GIC will produce this much money. And then when will this one produce that same amount of money? Well, we're going to put that 21,000 into here. So that A has been replaced with that because that's saying in this simple interest account, when will this produce that value? And then solving this, divided by 20,000 on each side, you get this. And now it's just basic algebra to solve for n here. And you can solve for n as 6.03. So again, half the money went in here, half the money went in here. This amount we can get. And then we're trying to ask, when does this become the same amount as this by setting these equal and solving. All right, hope that helps with that one. Let's look at the next one. In the next exercise, we had problem 1 here, and it was asking about something about, okay, so somebody's fighting an infection. Here's the number of white blood cells they have. The white blood cells are going down as the hours go up because they're taking antibiotics, and the white blood cell count goes down because white blood cell count went up to fight the infection. Now the antibiotics will fight the infection, so the white blood cell count is going down. It begins by saying create a general rule for this. All right, this might be strange, but let's take a look. Here we have our, let's say this is our U1 value and this is U2. Even though this is 12 hours later, we can say it's U2. That means each time you jump from U1, U2, U3, you're jumping 12 hours. So here's U1, so here's our U1, and to change this number into this number, we multiply it by the rate. And the rate is constant here. We find it by doing second term over first term. So the rate is 0.88. So we have this value, U1, times the rate, and T is however number of periods of 12 go by, right? This doesn't represent 1 hour. It represents 12-hour blocks because we said we jump from here to here to here. So here's our rule. And then it says, B, use the general rule to figure out what will happen. How many white blood cells will there be after 3 days? Well, after 3 days, we will have 72 hours passing, and 3 days on here will be like 6 of these 12-hour jumps, because that's 3 days. So you put a 6 in here and you calculate it. And I think the question was about C, and here's a good explanation of what the limitations are. This formula cannot be used forever because these will not forever go down, because eventually white blood cells will go back to a normal level because the infection has passed. So that's the limitation. That's what this one was asking for. All right, and the last one that everybody agreed was tough. We have a half-life of a substance. Half-life is the time it takes any radioactive isotope to decay and become half of what it was. So A just has you explain what's happening. If an isotope has a half-life of 1.23 years, it means it takes 1.23 years for it to become half of its weight or half of its mass. And that's what it explains here. B, write a general formula. This is, I think, where a lot of you got stuck. So this is just a geometric thing, right? Because every 1.23 years, it becomes half of what it was. So we have, this is what it will be, like our UN. This is the original amount, like our U1, let's say, like our starting amount. We call it A0 because it's the initial amount. And we multiply that 0.5 because every time a half-life cycle goes by, it becomes half of what it was, half, half, half. So 0.5 is our multiplier, our R value. Now this exponent is the tricky part. Basically, since it becomes half of its amount every 1.23 years, we need to put in the amount of years as a fraction here, because every time we put an amount of years in for t, it is saying what portion of the half-life have we completed. For example, let's say we have an original amount that was 1,000. If it took 1.3 years, so here's the original of 1,000. If it took 1.23 years, so we replaced the t with that, if that much time passed, then this would become 1, and then we'd have 1,000 times 0.5, which is 500. So that explains why this must be set up like this because that creates what we need, the half amount. Here's the answer for the rest. Check it out.